Hello everyone, I welcome you all to Startup Academy, your online gateway to success in ISS exam. This academy is exclusively for ISS exam only. And we have been preparing for ISS 2026 exam. We have covered the one of the major topics of this exam, which is econometrics, which is considered very difficult. In the previous lecture, we have covered econometrics and we have started another topic, which is sampling. I hope you have watched the two videos of basics of sampling, and the first one is simple random sampling with replacement and simple random sampling without replacements, their variances and their mean estimation, everything. Today we will continue with these two sampling only, simple random sampling with replacement and simple random sampling without replacement, and we'll cover a PYQ as well. So let us begin. So in yesterday's class, we have done estimation of sample mean and variance of sample mean, and their estimation of variance of sample mean, all those things, uh, of population mean. Today we will cover estimation of sample mean. Sample variance. Now we know that if we write estimation of sample variance, it is nothing but estimation of 1 upon n minus 1 summation I goes from 1 to n yi minus y bar whole square. This is the estimation. Now we can take out 1 upon n minus 1 outside of this term, and estimation of summation I goes from 1 to n yi minus y bar whole square can be written as 1 upon n minus 1 estimation of summation I goes from 1 to n yi square minus n y bar square. And taking in the estimation, we will get 1 upon n minus 1 estimation of summation I goes from 1 to n estimation of yi square minus n estimation of y bar square. Now we know one of the properties of estimation or variances is variance of x is equals to estimation of x minus estimation of x whole square, x square. So in estimation of x square can be written as variance of x plus estimation of x whole square, right? So substituting this value here and here, we will get estimation of s square is nothing but 1 upon n minus 1 bracket summation I goes from 1 to n. Now variance of y, if we say that estimation of yi square is equals to variance of yi plus estimation of yi whole square. We know that variance of yi is nothing but sigma square, and the estimation of yi is nothing but capital Y bar square. These two derivations we have done in yesterday's class, so you can look at that lecture if it is not understandable. So putting the values over here, sigma square plus capital Y bar square minus n variance of Y bar plus estimation of Y bar whole square. Yes. Now we will talk about simple random sampling with replacement and simple random sampling without replacement. First we will talk about simple random sampling with replacement. We know that here, so in simple random sampling with replacement, variance of Y bar with replacement. We calculated this, it is nothing but sigma square upon n, and estimation of Y bar is nothing but capital Y bar. So substituting the values here, we will get estimation of sample mean, which is small s square, is nothing but 1 upon n minus 1. Here n can be taken because there is no item, so n can be taken out of summation. N sigma square plus Y bar square minus n. Here it can be written as sigma square upon n minus plus Y bar square. On substituting, we will get this equation. Now opening the brackets, 1 upon n minus 1, n sigma square plus n Y bar square minus sigma square minus n Y bar square. So plus n Y bar square and minus n Y bar square gets cancelled, and we are left with 1 upon n minus 1 into n minus 1 sigma square. Taking sigma square common, we are left with n minus 1. So these two also get cancelled and we are left with sigma square. So here we can say in simple random sampling with replacement that sample mean is an unbiased estimator of population mean of simple random sampling with replacement. Sample mean is an unbiased estimator of population mean. Now moving on to simple random sampling without replacement. In simple random sampling without replacement, variance of Y bar without replacement is nothing but n minus n s square, and estimation of Y bar is nothing but capital Y bar. So now substituting the same in estimation of small s square, it is nothing but 1 upon n minus 1 n sigma square plus n Y bar square minus n. In the bracket we will write n minus n upon capital N small n s square minus n Y bar square. So here also plus n Y bar square and minus n Y bar square gets cancelled, and we are left with this. Now we know that yesterday we did that sigma square is nothing but capital N minus 1 upon capital N s square. We did this, so substituting this is as well here, we are left with small n into capital N minus 1 upon n s square minus, here n and n also gets cancelled, n minus 1 upon n s square. So taking s square and capital N out of here, so we are left with s square upon capital N into small n minus 1, n capital N minus n plus small. it is. So plus n minus n gets cancelled, and we are left with s square upon capital N n minus 1 into capital N n minus 1. These two also gets cancelled, and we are left with capital S square. So here also in simple random sampling without replacement, the sample variance is the unbiased estimator of the population variance, which is capital S square. So this has been proved. Now we will move forward that what is the calculating the unbiased estimator of variance of sample mean and variance of in simple random sampling with replacement and simple random sampling without replacement. So unbiased estimation of variance of y bar. So in simple random sampling without replacement, case 1, with replacement, we will calculate, we know that variance of y bar w with replacement is nothing but sigma square upon n. If we take estimation of variance of y bar w with replacement, then we will get estimation of sigma square upon n, which is nothing but 1 upon n estimation of sigma square, which is nothing but s square upon n. And hence we can say that the variance of y bar wr with replacement is nothing but the unbiased estimator of variance of y bar with replacement. So this is an unbiased estimator of variance of y bar with replacement. And similarly, in second case, in simple random sampling without replacement, we will get variance of y bar without replacement is nothing but capital N minus small n upon capital N s square. So if we take estimation of variance of y bar WOR cap, which is nothing but estimation of capital N minus small n upon n small s square, n minus n upon n estimation of small s square, which is nothing but capital N minus small n upon capital N small n capital S square. And hence we can say again that variance of y bar without replacement is an unbiased estimator of variance of y bar without replacement. Here it will be sigma square and s square. So this completes your topic, variance estimation of variance. Now we will move on further to confidence interval of mean. This is common in both simple random sampling with replacement and simple random sampling without replacement. So confidence interval of y bar. First of all, in case 1, when we assume that sigma square is known, if sigma square is known, then only one value is unknown. So we will take z test. So we can write z is equals to y bar minus capital Y bar upon under root of variance of y bar cap, which follows normal 0, 1. If this is the case, then 101 minus alpha percent confidence interval of y bar is given by probability that minus z alpha by 2 less than equal to y bar minus capital Y bar upon under root of variance y bar cap is less than equal to z alpha by 2, and this probability is given by 1 minus alpha. Okay, so now what is the confidence interval we get? We will get y bar plus minus z alpha by 2 under root of variance of y bar cap. This will be the confidence interval for when sigma square is known. Now the second case is when sigma square is unknown. Since we have two unknown quantities, then we will use t-test. So small t will be equal to y bar capital Y bar upon under root of variance of y bar, which follows t distribution with n minus 1 degrees of freedom. So 100 into 1 minus alpha percent confidence interval of y bar is given by probability minus t alpha by 2 is less than y bar minus capital Y bar upon under root of variance of y bar cap is less than equal to t alpha by 2 is equals to 1 minus alpha. So the confidence interval is given by y bar plus minus t alpha by 2 n minus 1 under root of variance of y bar. This is the confidence interval when sigma square is unknown. This completes your topic, simple random sampling with replacement and simple random sampling without replacement. Now, which one is better, simple random sampling with replacement or simple random sampling without replacement? For that, we have to calculate the efficiency between the two of them. Efficiency means variances, and the one whose variance is lesser, which is that becomes more efficient, and hence that is a better process or that is a better method as compared to the other one. So now we will find the comparison or efficiency between simple random sampling with replacement and simple random sampling without replacement. Now we know that variance of simple random sampling, variance of y bar with replacement is nothing but n minus 1 upon n s square, right? And variance of simple y bar without replacement is capital N minus n upon n capital S square. These are the variances which we calculated in yesterday's class, whose derivation we have done in yesterday's class, and it is very important. So now let us take variance of y bar with replacement. This is n minus 1 upon n capital S square. Now instead of this, I can also write it as n minus 1 minus n plus n minus 1. I have added n and subtracted n s square. So this can further be written as capital N minus small n upon n s square plus small n minus 1 upon n s square. We all know that small n is always greater than or equal to 1. So this will be either positive or 0. This whole term will be positive. So this states that variance of y bar with replacement. This formula is of variance of y bar without replacement. Variance of y bar without replacement plus a positive value. So we can state that variance of y bar with replacement is greater than equal to variance of y bar without replacement. Since variance of y bar without replacement is less than variance of y bar with replacement, we can say that simple random sampling without replacement is a better method, since variance of y bar without replacement is more efficient. More efficient, when does it become more efficient? When its variance is lesser than variance of y bar with replacement. So this completes your topic, simple random sampling with replacement and simple random sampling without replacement. अभी क्वेश्चन कराना है. So now we will cover a question of 2025, which is a PYQ, which came recently in your paper regarding the same topic, and it was of 15 marks. So the question says that has given us one five five so, one five sized population having 110, 60, 80, 20, and 30 observations. So we have to take a simple random sample of size small n equals to 2, and then from that population we have to prove that our variance of simple random sampling without replacement is more efficient for population mean as compared to simple random sampling with replacement. So on solving this, we know that capital N is given to as 5 and small n is given to as 2. Now we know that population mean, which is capital Y bar, is nothing but adding all the quantities and dividing by the total number of quantities divided by 5. 50 plus 80, 130, 130 and 170, 300 by 5, which gives us 60. So our y bar is 60. Now the next thing that we'll do is we'll calculate population variance, which is sigma square, which is nothing but 1 upon small n minus 1 summation I goes from 1 to n, 1 upon capital N minus 1, yi minus y bar whole square. So we will calculate this. Sigma square is equals to 1 upon 5 minus 1 is, the population mean is not capital N minus 1, it is only capital N. So it will be 5 only. Now summation of yi minus y bar. First one was 110 minus 60 whole square plus 110 minus 60 minus 60 whole square plus 80 minus 60 whole square plus 20 minus 60 whole square plus 30 minus 60 whole square. So on solving this, we will get 5400, and by cutting it down we will get 1080. Now we will find the value of, for simple random sampling with replacement, we will find the variance of simple random sampling, variance of y bar with replacement, which is nothing but 1 upon uh, the formula is sigma square upon small n. Now sigma square we have calculated is 1080 and small n is 2. So it will be 540. This will be the value of simple random sampling with replacement. And if we calculate for simple random sampling without replacement, our formula for n minus n upon n into s square. Now s square can be substituted in the form sigma square is nothing but n minus 1 upon n capital S square. So substituting this value, we'll get n minus n upon n into n upon capital N minus 1 sigma square. Capital N and small n gets cancelled and we are left with 1 upon n minus 1. Sigma square upon n. This can be written as sigma square upon n 1 minus n upon n. Small n upon capital N. On solving this, we will get this. So, putting the values here, sigma square was nothing but 1080 upon small n is 2, and this will be 1 minus 2 upon 5. So, this will be 540 into 3 by 5. Now, again dividing by 5. So, 5 ones are 5, zeros are 0, 5 eights are 40. 324. So variance of y bar with replacement is 540 and variance of y bar without replacement is 324. Now efficiency, calculating the efficiency. Variance of y bar with replacement upon variance of y bar without replacement is equals to 540 upon 324, which is almost equal to 1.67, which means efficiency of this is greater than 1, and hence we can say that variance of y bar without replacement is more efficient for population mean than variance of y bar with replacement. And this is what has been asked in the question, to prove using the given data to show that variance of simple random sampling without replacement is more efficient estimator of population mean as compared to variance of simple random sampling with replacement. So this completes your topic, simple random sampling with replacement and without replacement. Now from tomorrow onwards, we will move to another sampling technique, and I hope you are doing what we have done in class, consistently doing it on a regular basis. If you will continue doing it on a regular basis, then only you'll be able to clear the exam. If you leave gaps in between, then it is worthless for doing. So keep on doing it and keep on working hard. Thank you.